Okay, so let's start our tonight's class. Good evening, everyone, and welcome to our seventh lecture in BSE 534, Legislation Aspect of Fire Safety Management. And today we will have discussion on the topic of risk analysis and assessment in fire safety management. So over the next 3 hours, we will move from fundamental concept to some mathematical model, and with the aim of understanding how we quantify, evaluate, and manage fire risk. So to navigate our session today, we will follow a clear 5-part structure. So we will begin by introducing the core concept of fire risk. This is to establish a common language and mindset for our next hours. Then we will explore the diverse method of fire risk analysis, from some simple quantitative tools to some complicated quantified functions. And the crucial part of this journey is to understand the reliability of fire safety engineering. So then we will formalize this reliability by using some probabilistic model, and that allow us to handle the uncertainty mathematically. And finally, we will focus on life risk analysis. And in this part, we will quantify the impact of our decision on human safety. So each level provides the foundation for the next, forming in a comprehensive understanding in our risk-informed decision making. So this is the first part of our class. Building on our overview, now let's start with a foundation understanding of the core concept. What is the risk? So the risk is defined by the potential for controlled loss of something of value. So this something of value is very crucial. So it isn't just about money or properties. It can be human life, can be health, and can be some business continuity or even environmental well-beings. So when we apply this foundation concept to our domain, we arrive at a powerful and actionable definition of fire risk. So the fire risk tells us that every single decision we make related to fire safety is a fire risk decision. So consider a decision to use a certain type of coating for a high-rise building. This is fire risk decision. And the design for an emergency exit route in a shopping mall is also our fire risk decision. Even the frequency of the fire drill practice in an office is also our fire risk decision. So we are constantly making choices that either increase, decrease, or maintain a certain level of risk. And however, we must move towards a more scientific and quantitative approach. This is why we will explore engineering tools in this course. They provide the structure and the analytical context we need to move from asking what should we do to being able to demonstrate this is the most effective course of action. Now we have established that every fire safety decision is a kind of risk decision. So let's break down the mental framework we use to structure our thinking. So this is captured by 3 simple questions. So the first question is, what will happen? So this is where we move from a risk concern to a defined scenario. So we identify the specific sequence of the event of a kind of fire scenario. So this involves the hazard, that is the condition with the potential to cause harm. So imagine we are assessing a university student dormitory. To answer what would happen, we must identify a scenario where a student falls asleep while charging their phone on their bed, leading to a bedding overheating and igniting. So this defined our specific scenario and identified the hazard. An electrical device placed on a combustible material. So the second question will be, how bad will it be? Here, we analyze the consequence. We look at the expected effect of our scenario. So this include the direct loss. So what is the direct loss? Like the destruction of the student's room and the contents, and crucially, the indirect loss. The indirect loss in our dormitory example will be the severe reputational damage to the university or some potential legal liabilities and the displacement of other students due to the smoke and the water damage. So this is far beyond the initial flame, right? And finally, we will ask how likely it is. So this is the most important part. And in this part, we estimate the probability. So we need to quantify the likelihood of this specific loss scenario occurring. Based on data, we might estimate that for a dormitory of 500 students, the probability of a fire starting in this manner is, for instance, once every 10 years. So this is measured as a probability, giving us a numerical sense of the risk frequency. So by systematically answering these three questions, what and how bad and how likely, we transform a general worry about fire into a specific and manageable risk profile. Okay, so we need a practical tool to bring the answer together and help us to visualize the risk. So this is where the risk matrix come into play. So this is our risk matrix. Let's break it down. The matrix is a very simple but powerful grid. So on one axis, we have frequency, which answers how likely, the question of how likely. And it ranges from events that are so rare, we consider them of beyond extremely likely, perhaps a 1 in a million years event, and to a very high frequency. This frequency, we call it anticipated, and could happen multiple times a year. And on the other axis, we have what? We have consequence. The consequence answers how bad it will be. So this scale from negligible impact to a very high impact, like minor property damage to some would involve catastrophic loss, such as the total loss of a critical facilities. So where these two dimensions intersect on the metric give us our risk rating. For example, an event that is anticipated, that is a very high frequency to happen and has a very high consequence, will give us the number of 1 of the grid. So this is classified as high risk. So this is a kind of risk that demands immediate action. Let's consider a real-world application. So we imagine a large chemical plant. A very small contained fire in a maintenance workshop might be a frequent event, but with low consequence. So which grade it will be fall in? So that is very anticipate, right? But with low consequence, so it will fall in the matrix of grade of number 3. So this is a kind of moderate risk. Okay, so now let's give some terminology of our fire risk analysis. So the most critical distinction to make it between is a hazard and a risk. So what is the hazard? The hazard is an inherent and unchanging condition with the potential to cause harm. Think of a gasoline in a service station storage tank. So this is a hazard. But the risk, however, is the potential of that hazard to actually realize and cause unwanted consequence. So the gasoline is the hazard, but the risk is the chance that it might ignite and result in a fire, causing injury and damage. So that is the risk. So to quantify the risk, we always use two key components. The one is probability. The probability gives us the mathematical language to express how likely an event is over in the long run, allowing us to handle uncertainty consistently. And another one, the consequent, is the measure of the expected effects. That is answer our question about how bad. So if that event were to occur, we must be aware of the perceived risk. So this kind of perceived risk explained by our people. So it is decided by people faced with the same objective risk data. Something like when two people face the risk of flying or with the driving, they may have very different feeling about which one is more dangerous. So understand this human element is our perceived risk and will give our effective communication and management on our fire risk analysis. So all of these brought together is our risk analysis. And the systematic process of examining all these elements is to understand and manage negative outcome. So building on this, the fire risk assessment is the process of establishing information about what level of risk are acceptable. It should be noted that this is a kind of what level of risk are acceptable. So this involves risk estimation. It is a kind of scientific determination of the risk characteristic, and also the risk evaluation, which is the judgment on the significance and the acceptability of the risk. So this brings us to a critical truth that zero risk is not an achievable goal. Our aim is not elimination, but management. So there is no single universally acceptable level of fire risk. It is a kind of fluid concept shaped by technical, by society, and also by economic factors. So how do we define acceptable? Accepting a level of risk is a value judgment, and the different groups of people will judge it differently. So we can view this through four distinct perspectives for our acceptable. The first one is technically, and the technical expert, the general public, and the enforcer, and the final one, what kind of this? Managerial. This kind of professional, like a property developer, will construct our acceptable. So let's think of an example. The debate over mandating a kind of residential sprinkler. So let's explore how each group view the same issue. So from our technical judgment, the judgment is very clear. the expert obtain data from fire tests and some other computational simulations can demonstrate that the residential sprinkler significantly reduce the calculated fire risk. So they agree that with the residential sprinkler, they can get the more fire safety. So their decision is driven by the data on the risk reduction. But how about the general public? For the public judgment, however, it operates with a different calculation. They are balancing the benefits, the cost, and the risk of the full range of activities in their daily life. So when considering residential sprinklers, they are more likely to attach greater importance to the cost, and they may significantly underestimate the reduced risk the sprinkler can provide. So their judgment is often more influenced by immediate cost than by the statistic benefit. And then we come to the enforcer. The enforcer is a role often filled by fire safety engineers or building code officials. So their job is particularly tough because they have to navigate particularly between two very different worlds. So on the one side, they have the hard technical data from the expertise, which clearly show that the safety measures like the residential sprinkler can save lives. But on the other hand, they face the real world concern of the public, who may be worried about the cost. So the enforcer has to ask the difficult practical question that bridge this gap. Is it truly fair to make every homeowner pay for the sprinkler system? If not, who should bear the cost? And if we do require them, who ensure they will still work correctly in next 20 years? This is the enforcer judgment. So the enforcer judgment isn't just about the best technical solutions. It is about to find the balance of the solution, about the fire risk and the cost. So the finally is when it is about the management professional, or something like the architect, the builder, or the facility manager. So they make judgment heavily influenced by budget and the operational constraints. So their primary responsibility is to deliver a project or manage an asset within specific financial boundaries, right? So I think maybe one of you are like this kind of roles in a building or in some managed professionals. So their perspective on residential sprinkler will be directly affected by some cost and often more than by the benefits. So understanding these four perspectives is very essential for anyone hoping to successfully implement a fire safety measure, as you must navigate this landscape of conflicting values. So what does a fire risk analysis actually look like in practice? It is a systematic five-step circle that takes us from problem identification to a final decision. So the process begins by systematically identifying all potential fire hazards within a given space. Once we know what we are dealing with, we then work to quantify both the potential consequence of each hazard and we need to quantify its probability of occurring. So this gives us a clear picture of the risks we faced. And with that understanding, we can then brainstorm and identify various options to control this hazard. And the next crucial step is what? Is to quantify how much each of these control options would actually reduce the original risk. So this allows for a direct comparison of their effectiveness. And finally, we are going to select the most appropriate protecting strategy. That is a decision that is now informed by a clear analysis of data, something like the cost, the benefits, and most importantly, the level of safety achieved. So now, where we get the data to feed our analysis, this is a very vital result. A statistic information published by our own Hong Kong Fire Service Department. And this is their annual report. It provides a wealth of real-world data of the fire calls, special service calls, and the other false alarm. So for instance, by analyzing trends over several years, we can identify if a certain type of fire are becoming more prevalent, which in turn help us to enhance our research. So this is a kind of like empirical evidence of how fire risk happen in our city. So please remember, it is a kind of empirical evidence, not the kind of mathematical function. This real-world data from the Hong Kong Fire Service Department tell us a very clear story. So when we examine where the fire happens, we see a dominant pattern. The vast majority occur in domestic buildings. We can see that in the domestic building, we have more than 1,000 occurring in 2023. And the causes of this fire are equally revealing. They are not real events, but common ones. Primarily the stove overcooking and the general electrical fault. So our strategy should transfer from reacting to unusual catastrophes to managing everyday risk through the public education and the standards. And with that data and a structured process, we now turn to the method that we can use. Our toolkit is the board, and we have some non-quantitative approach like checklist and narratives, which are very simple for us. And we also have quantitative approach like indexing and the probabilistic method, which will provide numerical data. So the choice of the method depends on the complexity of our situation and the decision that need to be made. So the first one, it is a kind of non-quantitative method. It's the checklist. The checklist is a common accessory in fire safety, listing the hazard and the recommended practices. It is very practical, easy to interpret, and excellent for ensuring basic compliance during an inspection. For example, a checklist will ensure that the fire extinguisher are present and the emergency exits are very clear. This is all included in the checklist. But the major disadvantage of the checklist is that it treats risk in isolation. A checklist might confirm that all individual items are compliant, but it cannot capture how this factor interacts. It will not tell you how a blocked corridor might compound a risk posed by a slow-burning fire in a storage room. So this is a good starting point, but insufficient for many complicated risk assessment. But even a very more simpler are narratives. Narratives, it is a set of do's and don'ts. It is probably the earlier form of the fire safety advice we all receive from our parents telling us not to play with matches. So they are much less formal than checklists and typically only result in a pass or a fail with no evaluation. So now we move to some quantitative approach. A significant setup is indexing. So this is where we begin our true quantitative fire risk assessment. By using the rating schedules and the point schemes, we can get the fire risk assessments quantitatively. The fire risk indexing assigns numerical values to a selected fire variable based on some professional judgment and the past experience. So we might give a score for occupant load, another for the quality of the alarm system. And also we can combining these scores together, we arrive at a single fire risk index. It is a number that allowed us to compare the relative risk of different buildings or different rooms in a structured, consistent manner. So here is the risk matrix. As we can saw earlier, the risk matrix is a fantastic tool for visualizing the risk by providing a likelihood and severity. So this in one axis, it is a kind of probability axis, and the other one is for our losses. We can calculate it from high to low and also from high to low for our loss. Then we will give the number of different building of different fire scenarios and different discrete partitions. A more advanced and continuous analog is the risk counter. Think of these kind of lines connect the points of the equal risk level. So this allowed us to find a more clear understanding than the simple block of a matrix, especially when dealing with a continuum of possible outcomes. Okay, so this is our most important part today. It is the probability method. For the most informative and rigorous assessment, we turn to the probabilistic method. This approach allowed us to trace the value we produce all the way back to their fundamental assumption. So we have tools like event trees, mapping the possible sequence of events after the fire ignites. And we also have the fault trees, which work back from the system failure to find all its possible reasons. So they allowed us to model complicated systems and understand not just what might happen, but how likely it is to happen. So what is the key part of the probabilistic method? Anybody knows what is the key part of our probabilistic method? It is the probability distribution. So for example, this equation we're showing here describes an exponential distribution, which is often used to model the time to failure of a device. So it should be noted that the total probability, the area under this curve, must always equal to 1. And we can check at any time, we can check their failure of the device, the probability of this failure. So this is the probability distribution, and it is our heart of the probabilistic method. And it is vital to keep in mind that our models are built in a world of uncertainty. So this table contrasts a traditional performance-based design process with the one that explicitly incorporates uncertainty. We should notice that how step evolved. Instead of single design file scenario, we also develop a distribution of scenario. So we incorporate the uncertainty, and the uncertainty lead us to develop a distribution of the scenario, not just a scenario. So instead of a fixed performance criterion, we also use a probabilistic statement. So we will ask, does this design pass? No. So today we will ask how confident we are that this design will pass under a wide range of the plausible conditions. So we should have a concept of the what? Of the probability. So the probability is lead to the probability distribution. It is a kind of the failure of the risk with the time variations. Okay, so let's explore a powerful and practical tools in our risk analysis toolkit. That is the fire risk indexing. So what exactly it is? We can think of it as the crucial bridge that connects the theoretical file with the day-to-day needs of our fire safety decision. So it will provide a structured, cost-effective method for evaluating risk, making it invaluable for connecting research findings into a usable format, especially when we deal with complex system of the interacting components. So the mechanics of the indexing works by using knowledge-based rating schedule. This means we will assign numerical values to key variables, things like occupant load, presence of sprinklers, or complexity of escape routes, based on the professional judgment and the past experience. So these variables capture both positive safety features like the alarm system and the negative ones like the combustible material. So through a defined set of functions, these scores are combined together to produce a single and powerful number, the risk index. So this index will give us a straightforward, comparable measure of the risk associated with an entire facility. We can look at this spectrum of the risk quantification method, which should here by a curve A, B, and C. On the one hand, we have curve A. Curve A presents a full quantitative probabilistic risk analysis. So it is the most accurate approach because it is mathematically, and it will offer high sensitivity to differential even small change in risk. But it demands what? A large number of time, data, and the results. So in the other hand, we have the curve C. The curve C represents a very simple fire risk indexing. So the great strength of the curve C is its very low cost, and it can give us a very fast speed to make decision, making it perfect for screening a large number of buildings to quickly identify the high risk situation that need immediate attention. But the trade-off of the curve C is less sensitive. It is excellent for analyzing big problem, but may not reliable to distinguish between two similar low-risk buildings. So sometimes we can use curve A, but sometimes we can use curve C. It depends on your problem and the complexity of your problem. Okay, now let's examine a real-world application of the risk indexing, that is the fire safety evaluation system. The fire safety evaluation system is developed in 1970s, represents a sophisticated risk indexing approach that served as an alternative compliant path to the prescriptive life safety code. This brings us to the core innovations of FSES, that is, the equivalent concept. Rather than forcing older buildings to comply with every modern construction requirement, which can may be very expensive, the FSES provide a uniform method to demonstrate that alternative safety measure can achieve an equivalent level of safety. So this promotes the economic safety upgrades while maintaining or even enhancing the overall protection. So in the practical terms, FSES allows existing buildings to be judged on their actual performance capabilities. For example, an older hospital might not have the required corridor width by the modern standard. But if it has a superior smoke detection and also they have the sprinkler system, the FSES can mathematically demonstrate that these features will provide the equivalent life safety. So this performance-based approach enables a practical and cost-effective solution while ensuring we never compromise on safety. The FSES works by subdividing a building into the fire zones for evaluation. So we need to keep it in mind for this fire zone concept. A fire zone is a kind of space separated from other part of the building by floors, by fire barriers, and the smoke barriers. So this is a critical step because risk is not uniform throughout the building. So the fire safety challenge in the hospital are entirely different from those in a patient ward, and they should be evaluated separately. So this is why we introduce fire zone. We need to evaluate different zone by using different mathematical functions. So for each zone, the FSES begins by determining the occupancy risk. This quantifies the inherent risk deriving from the people who use the space. In our healthcare setting, it uses 5 parameters for our occupancy risk. That is patient mobility and the patient density and the fire zone location, the ratio of the patient to the attendance, and the final one, the average patient age. That is 5 parameters, and they all together will determine our risk index. For example, we can see that a zone with not mobile, we can see here, not mobile, it would receive a much higher risk factor than for the mobility one. For the mobility one, we have the risk factor of 1, but for that not mobile, we have the score of 3.2. So this is reasonable because if we if we evacuate a bedridden patient, it is far more challenging and more time sensitive. So the overall occupancy risk factor for this zone is calculated by the product of the assigned value for these 5 parameters. So this will give us a single number that represents the demand side of the safety equation. And another side is what? It's our supply side. Our supply side will be defined by another 13 5 safety parameters that representing the building's protective features. So the fundamental goals of the FSES is to ensure that the strength of the safety supply is sufficient to the occupancy risk factor. So this is our fire safety parameters. We have 3 fire safety parameters, cover a wide range of building features. The type of the construction, the interior finish, the presence of the sprinklers, smoke detectors, and the alarm systems. Each feature is assigned a positive or a negative score based on its capability. For instance, a building with non-combustible type 1 construction will score positive, but the one with unprotected combustible construction will have a negative score. So we notice that how the scoring reflects the real safety impact. Having incompleting corridor will give a significant minus 10 points. As you can see here, if the doors of the corridor is unfinished, it will be given a minus 10 score. So it reveals the real-world impact of these parameters. And these remaining parameters also covers the hazardous area and also the smoke control and the emergency routes and the alarm systems and the automatic sprinklers. So what makes it particularly sophisticated as their interaction rules down in the footnotes. So you can have this slide on our Blackboard, and you can give a look at this one for our how we can assign numbers to our fire safety parameters. So a key principle embedded in the system is what? It's the fire safety redundancy. The fire safety redundancy ensures that the failure of a single protection device does not lead to a major fire loss. So the 3 core strategies are shown here. The first one is the containment. The containment keeps the fire in its place of origin, and also the extinguishment. The extinguishment putting the fire out quickly, and also the people movement. The people movement ensures fire evacuation. So how these 13 safety parameters are strategically allocated across these 3 defense layers. So let's have an example here. We can imagine a hospital patient room fire. So for the containment, we rely on what? We rely on the construction type, right? Such as the corridor walls and the doors to prevent the fire spread. And the next, for the extinguishment. For the extinguishment, we have the automatic sprinklers and the smoke detectors. That is our way to keep the fire out. And the final one, we have the people movement. For the people movement, we will ensure that inadequate access and the emergency routes. So that is when our system fails, that the sprinklers don't activate, but the containment and the people movement system will still provide the protections. So as we mentioned before, the FSES quantified the 13 fire safety parameters by grouping the parameter score into these three categories. Each of one will give is the certain number by comparing each number from our compartment and our buildings. So the score from the relevant parameters are a summation to produce the three total values. So for S1 is what? S1 is for our containment, and the S2 is for our extinguishment safety, and the S3 is for our people movement safety. These totals are then compared against the minimum value required by the Life Safety Code. And this ensures that every building demonstrated adequate protection across all three critical safety strategies. And then we recognize that 13 parameters cannot cover everything. So the FSES includes the supplemental requirements, another 12 additional parameters to ensure that all aspects of the code are addressed. It is very interesting. So we have totally 25 parameters in our FSES. So furthermore, the process can be enhanced with such as a optimization technique, such as the linear programming. This is another very powerful mathematical approach to answer a critical management question. Given a limited budget, what is the optimal combination of our fire safety upgrades to achieve the greatest possible reduction in risk? So it moves us from the simple compliance to a strategy resource allocation. So you can think of it. What will be the objective function in our fire safety design? The objective function will be the design that we want to achieve. So the objective function should be the cost plus the acceptable safety level. And we also have our constraint. Here we have constraint 1 and the constraint 2, but in some real world applications, we will have too many constraints from our budget, from our, such as the building barrier, and for our risk judgment. And we need to get an objective function in this kind of feasible region, all under our constraint line. Then we will get our optimization strategy. Also, okay, so we talk about the FSES for such a long time. Then beyond the FSES, we can also structure the fire safety decision by using what? Hierarchical approach. So this makes us define levels from broad policy to specific survey item. Now let's look at a structured 5-step method. This is it constructs our hierarchical approach. So this approach systematically translates the high-level fire safety policy into specific actionable items. So firstly, you define your hierarchy of the decision making from the policy down to the objectives, like the strategies, attributes, and finally measurable survey items. And then you construct and assign numbers to each matrix that quantify the relationship between each sequential level. By multiplying these metrics together will give us a definitive importance that ranking for all the bottom level items, which is then verified for the practical sense. So that is an example for our hierarchical approach. This diagram shows the powerful matrix operation that brings the hierarchy to life. And we begin with what? We begin with the policy priority vector. This is the first vector we are looking for, a policy priority vector. And this vector multiplied by a relation matrix that quantifies how much each strategy contributes to achieving the policy objectives. And then the result is a new vector, a ranked list of the strategy. This ranked list of the strategy is weighted by their importance. Okay, and then we take this strategy importance vector to multiply it by the next matrix. This one defines how much specific parameter contribute to each strategy. And the final output, this one, what it will be. The final output is our ultimate guide, a clear ranking of all measurable safety parameters directly traceable back to our original policy. So let's take an example and imagine our policy is ensure safety evacuation of immobile hospital patient. So the key strategy would be the provide structure refuge. So the first metric will give this a very high importance weight. And this high weight strategy then flows into the next matrix, in which the parameters support structural refuge. The attributes like the fire door reliability would score very highly. So the final output will rank the fire door inspection as the top priority action items. So by using this strategy, we can break our policy down to each item. So this is our hierarchical approach. And the principle of our risk indexing and hierarchical decision making are very important. So they have been successfully applied in a wide range of areas, such as the healthcare facilities and the telecom center and some of the timber frame apartment buildings. So when we're selecting a fire risk ranking system, it must meet several criteria. So that brings us to another very important point, the criteria. So the criteria must be easy to apply and must be technically valid and consistent, transparent. The attributes it scores should represent the most frequent fire scenario, and their definition must be clear and operational. And also, the method should systematically handle subjective values and attribute interactions, and it must be thoroughly documented. The predictive capability of the criteria must be evaluated against the real-world outcomes. So a good system is not a black box. It is a transparent and justifiable tools. So it depends on our criteria. How we set our criteria will be very important part for our file risk indexing. Okay, let's break for 10 minutes, and after that, we will come to our reliability, which will be the most important part in our class today. Okay, take a break. Okay, so now we come to our three part of our today's class, the reliability of fire safety. So now we are focused on a concept that is absolutely fundamental to any quantitative risk assessment, that is reliability. So reliability asks the question about what it is the probability that this device or systems will perform its intent function under given condition or a specific period of time. So please take notes that we are consider about the probability. So the reliability is a simple but powerful concept. It is the ability of any item, a product, a component, or an entire systems to perform its required function under stated condition for a specific period of time. So we can look at this ability in two ways. The one way is the deterministic. We can use deterministic approach to ask how and why something fail, focusing on the physical mechanics. But for a quantitative risk analysis, we use another probabilistic approach, which allowed us to assign a numerical measure to that ability. So this is where we introduce the fundamental equation of our probabilistic reliability. So this expression R of t is the heart of the matter. So let's break it down carefully. This is read as the reliability of the item of time t is the probability that its time to fail, capital T, is greater than or equal to a specific mission time, given that certain operating conditions C1, C2 are present. So in a very simpler term, it answers a direct question: what is the chance of this component will still be working when we need it at a future time t? So the random so the random variable t is important here. The capital T is a kind of random variables, but it represents an item's failure time. So we can also model other failure models, such as the circle to failure for a mechanical concept. But in our fire safety, a crucial concept is the stress strength method, where the failure occurs when the stress on a system exceeds its strength. And we will have a detailed concept on this kind of method. And now you can please take this equation in mind. You should also be careful about this capital T, because this capital T is a kind of random variables, and it is very important in our fire safety components. So let's consider a practical examples. We can imagine a smoke detector in a hotel corridor, and we want to know its reliability for a mission time of such as 1 year. So 1 year is T is equal to what kind of hours? 8,760 hours, right? So the condition C1, C2 might include the ambient temperature and the dust level. So the time to failure, the capital T I mentioned above, is random. So we don't know what exactly it is. We don't know when exactly it will fail. So if the testing data tell us that 95 hours out of 100 hours, such detectors function can correctly after 1 year under those conditions. So we can say that the reliability can be RT equals to 0.95. We can use 95 divided by 100, and that will give us the probability. So the reliability will be that by using that definition. So we can mention about that the failure time capital T is also a random one, and we don't know how exactly when it will fail. So we need to keep some empirical data to get the failure time of capital T. So the reliability function will be a kind of likelihood of the failure probability distribution functions. So let's formulate it with a mathematical function. We can start with the probability density function, ft. So we can think of it as a curve that describes the likelihood of a failure occurring at any specific time t. So the shape of this curve is determined by everything about the item, such as its designs and how it operated and the environment it is in. So if we want to know the probability that the item fails on or before a certain time t, we look at the area under this ft curve from 0 up to that time t, right? From here to here. We need to calculate the area under this curve. So this cumulative probability is called the reliability function, capital FT, capital FT. And it is calculated by integrating f theta from 0 to t. So it have another name. What kind of name it is? Cumulative distribution function. So we have the probability distribution function and the integrating the probability distribution function, we can get the cumulative distribution function. So it will give the area under this curve. And that is our unreliable function. But if we consider about the reliable function, so what it will be? So the reliable function can be written as RT equal to 1 minus capital FT. That will give us our reliable function. And it is the area under the curve on the right side. So it can also be calculated by using the integral of f theta from t to infinite. Remember our capital FT. Capital FT is the integrate of the f theta from 0 to t, right? And here we can use 1 minus capital FT, and we can get the integral from t to infinite. So this is where the reliability function RT comes in. So it is the probability that the item is still functioning at time t. And logically, if capital FT is the probability of failure, then the RT must be complement by 1 minus capital FT. And graphically, this represents the area under the FT curve from t all the way to the infinite. So let's make this concrete with an example. And imagine we have a specific model for a smoke detector. The function ft describes how its failure rate is distributed over, let's say, 10 years. And perhaps a few fail in year 1, but most start to fail as they reached year 8. And now if we want to know the probability that a randomly selected detector will fail within its first 2 years, we could calculate F2. Now the T become 2. And conversely, the manufacturer's reputation relies on the probability that it won't fail in that time, which is the reliability, R2. So R2 equal to 1 minus F2. And if F2 is such as, let's say 5%, then R2 will be 95%, right? Meaning that we can be 95% confident that it will work when needed during the first 2 years. So you can take notes on this slide, and I think it will be shown in our final examination. Okay, so we often use a single and a summary measure to communicate reliability. And the most common one is the mean time to failure, that is MTTF. So the mathematically, mean time to failure is the expected value of the time to failure random variable, founded by integrating t multiplied by ft from 0 to infinity. So it is the average lifetime you'd expect from a population of non-repairable items. So for our smoke detector example, the mean time to failure might be 7 years. And a related but critical different term is what? It's the mean time between failure. The mean time between failure apply to repairable system and includes not just the time to failure, but also the time to discover the failure and repair it and get the system running again until the next failure. So this is a very similar but different concept, mean time to failure and the mean time between failure. Okay, now let's come to our most important part, that is the stress-strength interference model. The stress-strength interference model, we can give an example. Imagine any component in a system, and during its operation, it experiences external demands like what? Heat, pressure, or loading. We call this as stress. And at the same time, the component itself has an inherent capacity to resist the demand, which we call it strength. The failure occurs in a very simple but the binary way. That is, when the applied stress exceeds the component's strength. Now, in a real world, neither of these are fixed number. The stress can vary. Think of a different heat intensity in a fire. And the strength can also be vary due to manufacturing tolerance or material characteristics. So we model both strength and the stress as random variables. This is where our interference comes in. Reliability is the probability that the strength distribution stay above the stress distribution, and where these two distribution interfere or overlap, that is the probability of our failure. So this slide presents a mathematical core of the stress-strength interference model, and we will break it down from the simpler case to a more complicated case. So now let's start with the top scenario, a random stress and a fixed strength. Here, our strength is a known constant value of S0, and think of this as such as a perfectly predictable threshold, like the specific melting point of a standard material. But the stress S, however, is random and follows a probability density function Fs. This function Fs describes the likelihood of different stress level occurring. So the question is, what is the probability that the random stress will be less than our fixed strength? This probability is our reliability, right? So mathematically, we find this by calculating the area under the stress probability curve, Fs, for all values of S that are less than S0. All the value of S are less than S0. So this is exactly what the cumulative distribution function gives us. So that formulation, S is less than S0, would be a integration of SFFS ds from what? From minus infinite to S0. And if we use most commonly used one, we can get this kind of formulation. We use 1 minus another part of the integral, that is from S0 to infinite. So the formula calculates this exactly area, the probability of success. And if we frame it from the failure perspective, we can use the second equation to calculate our reliability. So this kind of formula will yield our probability of success. And this is a very simple cases for our stress-strength interference model. And now we have more complicated model. We have the random stress S, and we also have the random strength. So the random strength, we can use the probability function of Fr to represent its probability distribution. So what will be our reliability? We want to know that the stress S is less than strength R, but both of these functions are random selected. So how can we get this probability? So we must consider all possible pair of S and R and sum up the probability of all pairs where S is less than R, right? So this is what the double integral accomplished. We have the double integral. So let's firstly look at the internal integral. We have the internal integral, we have what? We have FSR. And we ask for a fixed value of strength R. What is the probability that the stress S falls between 0 and that specific R? It calculates the probability of success for a given R. So that is why we have the integral upper limited of R. It is a value, a fixed value. Then we extend it to a outer integral. The outer integral then sums all these conditions probability over all possible value of the strength R, each of them weighted by their likelihood. So that will give us the first equation shown here. And we can also have another, happen here. So we can also have it in another aspect. So what is this? The second form. The second form, if you look at it, you can find that the position of ds and dr is transverse. And the upper limit and the upper limit of our integral is also transverse. What does it mean? So for the inner integral in our second formula, we ask For a fixed value of stress S, what is the probability that the stress R is greater than this S? It is the probability that the component survive a specific stress level. And the outer integral then sum this all over the possible stress level. So that will give us the second formula. And we also should be noted that the FSR can be equal to Fs multiplied with Fr. It is very crucial because it states what? It states a kind of independent random variables. That means our stress and our strength are independent. So the probability of a certain stress level occurring is not influenced by the strength of the component. This allowed us to separate our joint probability into a simple product of their individual probability, and which will greatly simplify the calculation. So you can take a note to the first formula of this random stress and the random strength. So here we have given our stress strength model for both two cases. And now we can refine the stress strength model with a more powerful mathematical formula. And here we defined a new crucial random variables z, which is equal to r minus s. So what does it mean in our real-world application? We call z as the safety margin because it equal to r minus s, means our level of the strength that is more over to the level of stress. So this single variable represents the entire safety of the component. If z is positive, we have a safe state. But if z is negative, some failure will occur. So that will allow us to re-express the reliability function. Since the reliability is the probability that strength exceeds the stress, P as less than R, so it is now equivalent to the probability that the safety margin Z is greater than 0, right? So we can have the second formula here. And we can also use what? Use a kind of cumulative distribution function to find the z in this situation. Because each of the probability of z greater than 0 can be reformulated by 1 minus the function of z less than 0. And if we consider about the probability of z less than 0, it will give us a cumulative distribution function. So this where is our cumulative distribution function of z can be found, and we will not give so much detail here. Okay, so this graph is a classic material stress strain curve, and it can help us visualize the concept of the stress and the failure on a fundamental level. So we can have the yield strength here, the yield strength in the very early of the strain. The yield strength is the point where the material begins to deform permanently. And the tensile stress here, this point, is its ultimate capacity before fracture. So in our stress strength model, the applied stress would be a value on the y-axis. If that stress across the yield point, the component may have undergone permanent and damaging deformation, a form of failure. And if it reaches the tensile stress, we will observe catastrophic rupture. So this underscore that strength isn't a single number. It is a defined limit based on what we consider of the functional failure. Okay, so let's take an example. Let's consider a fire safety for a fire door and its frame. So what's the stress? The stress is the heat and the pressure from a fully developed fire from one side to the other side of the door. And it is not a single temperature. It is a random variable. So it follows a probability distribution Fs based on different possible fire scenarios. And then we consider about the strength. So what is the strength? It is the door's fire resistance rating. Let's say it is the ability to withstand heat for 60 minutes, but not every door is identical. Due to different manufacturing and installation such as the actual failure temperature of the population of 60-minute door is also a random variable with its own distribution of FR. So the reliability of the door is not a guarantee. It is the probability that for any given fire and any given door, the door's actual strength, let's say it's random R, is greater than its actual stress, let's say it's random S. So if the tail of the high stress fire distribution overlap with the tail of the low strength door, that is the interference region, and that is where our failure occur. Okay, so building on our understanding of the reliable function RT and the failure probability distribution function of FT, we now introduce a critical important function, the hazard rate, or HT. We can think of it in this way. The RT, the reliable function, tell us the probability a new component survives to time t. But what if the component has already been operating successfully up to time t? We need a measure of its immediate risk of failure. So that is precisely what the hazard rate gives us. Formally, HT is the instantaneous failure rate, and it represents the conditional probability that a component which has survived up to time t will fail in the next very small instant of time. So please remember, it is a kind of conditional probability. So here will give us the failure rate and the hazard rate. Okay, so we can define a simple average failure rate over a period delta t. But the hazard rate is this very concept taken to the limit as delta t approaches to zero. So this gives us the instantaneous risk at any moment. And the mathematical relation is what? Ht equals to Ft over Rt. So the numerator Ft, as we mentioned before, is the unconditional probability density of the failure around the time t. And the denominator Rt is the probability that the component has survived up to time t and is therefore at risk. So the hazard risk hazard rate is the density of the failure relative to the population that is still surviving. So let's take a quick note. The hazard rate is typically used for non-repairable item, focusing on the first and the only failure. But the failure rate is often used for repairable item, describing the rate of occurrence over their entire life cycle. So this example is also very important for our understanding the failure rate and the hazard rate. So let's see how HT behave over the lifetime of many components. So in practice, the hazard rate often follows a very distinct pattern known as bathtub curve. This curve is divided into 3 characteristic regions, and understanding them is the key to effective maintenance and safety planning. So let's take a look at this bathtub curve. So the first region is what? The burning failure. The burning failure is it's very high but decreasing. So think of why the burning failure is very high but decreasing. So this is due to our early failure caused by the latence defect, such as the faulty manufacturing and the poor installation or the some substandard materials that we used. So the components that survive this initial period are very proven. So we have a very high but decreased hazard rate. And the next region will be the chance failure or useful life region. So this is the period of the stable, lower, and the constant hazard rate. The failures here are not due to age or defects, but random, some unpredictable events like the power surge or an accidental overload. So this is the prime of our component's life. And finally, we have the wear out region. And here, the hazard rate begins to increase rapidly due to their aging phenomenon, such as the material fatigue, corrosion, or some of the cumulative wear and tear. So the components are simply reaching the end of their service life. Okay, so let's consider a real-world example for such as an automatic fire pump in a high-rise building. So in the burning phases, it is shortly after installation, and there is a higher chance of failure. Perhaps a seal wasn't fitted correctly, or a wiring connection is loose. So these issues tend to show up quickly. And then we have our chance failure phase. For years afterward, the pump operates reliable. Its hazard rate is very low and constant. A failure in this period might be caused by a random event like a foreign object entering the water. And after 15 to 20 years, the risk begin to climb again. The impeller corrode and the motor installation degrades, so the component is no longer as resilient as it once was. So that helps us to understand our failure rate and the hazard rate. So now let's come to our mathematical relation for our failure rate and the hazard rate. It is a very important part to understand our failure rate and how we can calculate it. So we define the hazard rate HT and the reliability function RT. This slide reveals the mathematical relation that bind them together. So we begin with the fundamental definition. The fundamental definition is that the hazard rate is the failure density divided by the survival density. The failure density divided by the survival probability, right? So HT equals to FT over RT. And we also know that the unreliability, capital FT, is simply 1 minus 1 minus the reliability. So RT equals to 1 minus capital FT, right? Now let's look at the differential, DRT. The DRT is what? DRT is the R, since we have the RT equals to 1 minus capital FT, so the derivative of RT is equals to minus D capital FT. And the minus D capital FT equals to minus FT. Why is that? Why is that? Anybody knows why is that? Because FT is the derivative of the capital FT. Or we can call it in another way, that the capital FT is the primitive function of the FT. So we can have this function here, and we can calculate DRT as minus FT. So then we can substitute this minus DRT into the numerator of our function. Then we can get this one. We can get this cumulative hazard function up to time t. So anybody knows why we have this function? Think of it. It is a very simple mathematical transformation. I believe you have learned it before. Because when we integrate the hazard rate, we substitute Ft with minus dRt in the definition of Ht, and this can be rearranged as Ht equals to what? Minus dRt over Rt. And the right-hand side, minus dRt over Rt, is recognized as the derivative of minus ln Rt. So we have Ht equals to what? Equals to minus ln Rt. So now we can integrate both sides from time 0 to time t. So on the left, we get the cumulative hazard function, and that is the least function. And on the right hand, we integrate the derivative, and which give us the minus ln Rt plus ln R0. So that means we need to find what? We need to find the primitive function. We need to find the derivative function, and we need to find the primitive function of ft and rt. We need to know that the relation between these two functions, and we can get the transformation between them. Then, when we do our integration for ht, we can use this kind of transformation to get the final result of the function. So that is our cumulative hazard function. Okay, so where we apply a logical and a powerful assumption is at time 0, a new component is perfectly functional. So that means what? That means our R0 equals to 1, right? Because it is totally reliable. So R0 equals to 1, and the ln R0 equals to ln 1. Ln 1 equals to what? 0. So this simplifies our equation. So we have this equation under this assumption that our cumulative hazard function can only be written by using minus ln RT. And please keep this function in mind. And use this function, we can also get transformed for our RT. So the integral from 0 to time t of hx dx represents the total risk burden the component has been exposed to from time to 0. And the exponential decay captures the idea that as this accumulated risk increase, the probability of the survive decrease. So this kind of transformation will tell us this truth in a real world application. And in here, we can keep this equation in mind. Okay, any questions for our formulation? Okay, so this diagram also serves as a quick review for our stress strength model, reminding us that the failure is not a certainty but a probability, and will be determined by the interplay between the demands placed on a system and its inherent capabilities. Okay, so let's take a 10 minutes break, and if you have any questions about the formula for our hazard rate or failure rate, please feel free to ask. Okay, take a break. Okay, so let's continue our class. In the last class, we talk about the failure probabilistic. And in order to model our failure probabilities we have been discussing, we will use some specific probability distribution. So in this class, we will introduce these three most commonly used probability distribution in reliability engineering. That is, the first one, exponential distribution, and the log normal distribution, and the Weber distribution. So the first one is exponential distribution. The exponential distribution is a one parameter distribution that characteristic by a constant hazard rate. It is widely used to model the time to failure of electronic components or some complex system during their useful time, where the failure rate does not change significantly with time. So it is so the simplicity of this exponential distribution make it a good first approximate for many reliable calculations. So here we can see that a kind of one parameter probability distribution ft equals to lambda times exponent of minus lambda t. That is a very commonly used probability distribution function, and it have this kind of curve for their relation between the distribution function over the time. And the next one is the normal distribution. The normal distribution is the very fundamental probability distribution in all of the engineering and the statistic. The normal distribution, and its characteristic is the bell-shaped curve, as we can see in the figure, the bell-shaped curve. The bell-shaped curve appears everywhere, from natural phenomenon to some measurement error. So we have two key forms present here. The first one is the standard normal distribution. So in the standard normal distribution, we have the equation of f of z. So in this form, the random variable z has the mean of 0 and have a standard deviation of 1. So this is a very convenient standardized reference curve. But the more general used form is the normal distribution for any random variable of x. So in this equation, f of x is defined by using two parameters. Mu is the mean, which controls the center of the bell curve, and the sigma is what? It's the standard deviation, which controls its width or dispersion. So we should notice that the relation between the two, the normal distribution, the standard normal distribution, and the generally used normal distribution, it is because that the variable x and the variable z can be transformed between these two kind of distribution. And if we use the standard normal variable z, can be used the formula of x equals to what? Equals to sigma z plus mu. So this process is called what? It's called the standardized. The crucial point about the general equation is the scaling factor in the red box. That is the 1 over sigma times the square root of 2 pi. So this scaling factor ensures that the total area under the probability density curve equals to 1, which is the fundamental requirement of any probability distribution. So without the scaling, the integral will not be unity. And this graph on the side illustrates the effect of this parameter. We can see multiple bell curves. So firstly, we should notice that the different line showing how the mean, what is mean, the mu, shift the entire distribution along the x-axis. For instance, this could represent the average birth weight in different populations. And more importantly, we see how the standard deviation, sigma, change the shape. We can see if we have a very small sigma like 0.2, will result in a tall, narrow curve, indicating that the data points are tightly clustered around the mean. But if we have a large sigma, like 1 or 5, will result in a short, wild curve that indicating the data is much more spread out. So for a fire safety context, we might see a normal distribution applied to the strength of a batch of steel beam. The mean strength would be mu, and the variation due to the manufacturing process would be captured by sigma. So understanding distribution is the first step in our performing a stress strength analysis. And here it's often used for modeling the distribution of a component's strength or stress intensity. So for example, the activation temperature of a large batch of links in the sprinkler might be normally distributed around a mean value. And this standard normal table allowed us to easily calculate probabilities associated with any normal distribution. And the next one is log normal distribution. So what does it mean? Log normal distribution. It is very useful for modeling failure times that are the product of several random factors. So if a variable is log normally distributed, that means its logarithm is normally distributed. So it is often used to represent repair time of process where the failure results from an accumulation of damage such as crack growth in a structural element under a cyclic loading. So this is a different shape of log normal distribution that is controlled by the value of sigma. And the next one, we have Weber function. The Weber distribution. It is primarily application is to represent the time to failure for a component or system. And if we let the continuous random variable capital T be the time from a start point until a component fails. So the Weber function will provide a powerful model for its probability density. So its formula comes from its three parameters. As we can see in the formula here, we have the three parameters. The parameter alpha is the scale parameter, and the parameter beta is the shape parameter, which controls the very shape of the failure rate, allowing the distribution to model a wide variety of failure behaviors. And in many practical applications, we assume that the failure can start from time 0. So this allows us to simplify the model by setting the location parameter gamma equal 0. Let's say we have gamma here, we have gamma in the first formula here and the second term here. But we have, if we set the gamma into 0, we can get a very simple formulation as this form. So this gives us a much more common two-parameter Weibull distribution. The formula becomes more manageable, and this version is most frequently applied in the practice. So our focus now shifts entirely to understanding the powerful interplay between the remaining two parameters, the shape parameter beta and the scale parameter alpha. So now let's have this one. Firstly, the shape parameter beta. When beta is less than 1, what does it mean? We can have this curve. We can have this curve here. So if the beta is less than 1, the failure rate decreases with time. And this models a what? Early life failure. And if the beta equals to 1, the failure rate is constant, mostly constant. The distribution simplified to the exponential distribution, modeling a very random and age-independent failure. And when beta is greater than 1, we have what? The failure rate increases with time. This is the class wear-out phase, as we mentioned in our last class, where the component deteriorates during the age, fatigue, or cumulative damage. So the curve becomes this kind of bell-shaped with a positive scale. And the second, the scale parameter alpha, also known as the characteristic life. So it is not the mean, but a scale parameter that gives us a reference point on the time axis. So a large alpha stretches the distribution, indicating a longer life. Okay, so let's take an example from fire safety. Let's modeling a failure for a thermal fuse in an application. So for the early failure, that means the beta is less than 1. In the first few months, a few fuels might fail due to the manufacturing defects. So the failure rate is high initially, but decrease as the defective units are delayed. And for the next several years, as we mentioned before, we now come to the what? The random failure. The fuels fail only rarely and unpredictably, perhaps due to the random power surge. And for the third stage of the beta is greater than 1, let's say after 10 years, so the fuel's internal material begins to what? Begins to degrade due to some sustained thermal cycling. So the failure rate now increases steadily with time. So that is becomes our Weibull distribution for our real-world application. Okay, so now let's come to our system reliability. We have talked about the component reliability. How about the system reliability? So the system reliability, we can imagine a system like a series of components connected in a chain. So for the entire system to function, every single component must succeed. So this is a kind of a series system. There is no redundancy. That means the failure of any one component will cause the entire system to fail. So this chain is only as strong as its weakest link concept directly to the mathematical model. Since we need all components to work, and if we assume they fail independently, the system reliability, RST, what will it be? RST will be the product of the individual component reliability. So Notice that since each RIT, that means each component's reliability is less than 1, as we mentioned before, so the product is always less than the reliability of each of the components' reliability. So the system becomes less reliable with every additional component you added, because it is a kind of series system. And furthermore, if we express this in terms of the hazard rate, what it will be? The system's hazard rate, HST. So the HST becomes the summation of the individual hazard rate. In a series system, every component represents a potential point of failure. So the total system risk is the accumulation of all individual risks. And if the model becomes particularly powerful and simple, when we assume that each component has a constant hazard rate, denoted by lambda. So in this case, the reliability of each component follows an exponential distribution. So substituting the exponential model into our series system formula, we will see the product of the exponential becomes the exponential of the summation. So this will reveal a crucial insight that a series system of components with our constant failure rates also has a constant failure rate itself. So that means the system failure rate lambda s is the summation of the individual failure rates. So this leads directly to a key performance matrix that is our what we mentioned before, the mean time to failure, MTTFS. So for a system with a constant failure rate, the mean time to failure is simply and the reciprocal of the failure rates. That means the 1 over the lambda s. And you can also calculate it as 1 over the summation of each hazard rate of the component. So let's say if we have such as a series system, a basic file detection circuit in a series, we have a smoke detector, a control panel, and an alarm bell. So if the detector have a 5% chance to failure in a year, so and the panel has the 2% and the bell has a 1%. So what is the system's probability of the failure in 1 year? We can simply sum it up. That means 5 plus 2 plus 1%, right? So we can get the summation of the total components rate failure rate to get our system failure rate in 1 year. Okay, so let's consider a more complicated system, that is the parallel system. So the parallel system, that means each component can work independently. So the system will fail only if that every single component fails. So as long as at least one component is functioning, the system is optional. So the system is operational. So this is a class kind of redundancy design. So in our real world, we usually use this kind of parallel system because it's more stable and reliable. So the mathematics reflects this logic. As we can see the formula here, it is easier to first calculate the probability of the system failure Fs by using what? By using the product of each FIT. So what is the FST? FST is the probability that all units fail. and this is the product of their individual unreliabilities, right? So therefore, the system's reliability, we can simply use 1 minus this probability of total failure, right? This formula shows why redundancy is so powerful. Even if one component is moderately unreliable, we adding a second, the parallel component, we can increase the overall system reliability. Okay, now let's also think of an example. So there is a severe room with 2 independent power supply, and each of them connected to a different electrical grid. So the system, the severe room, only fails if both power supply A and the power supply B fails simultaneously. So the probability of both failing at once is much lower than the probability of one failing, making the system far more reliability than either component alone. But always we have our complex system. That means we have both series system and we have the parallel systems. They are complex systems that combine both configurations. So when we analyze this complex system, will require us to deconstruct the system into some smaller, manageable series and parallel blocks. We calculate the reliability of each block, and then we combine them to find the overall system reliability. So when we consider a more robust fire suppression system, it might have 2 independent detection paths. Path A is the heat detector and the alarm sounder. Working in parallel with another path, path B, we have the smoke detector and the alarm sounder. So what will be the reliability of this complex system? How can we calculate it? So we can easily firstly calculate the reliability of the series chains in path A, right? So the path A, the RA will be the R heat detector multiplied with the R sounder. And then we calculate the reliability of the series chains in path B. The RB will be equal to R smoke detector and R sounder. So we can treat path A and path B as a parallel system. That means our R system is equals to 1 minus what? Minus RA multiplied by RB. Is that correct? No, it's not correct. Because RA means the reliability of the path A, and the RB means the reliability of path B. But for our parallel system, we need to use 1 minus the unreliability of both path A and the path B. So we firstly calculate the unreliability of path A. That means the 1 minus RA. And also the unreliability of path B, that is the 1 minus RB. So we can calculate the R system that give us the 1 minus this multiple product of 1 minus RA multiplied by 1 minus RB. So I think it is a very clear and simple cases for your understanding. Okay, so after the system reliability, we have our life risk analysis. So the life risk analysis is the ultimate application of everything we learned. So we focus our analytical tools on the most important consequence, the risk to human life. So the central thesis is clear. The earlier fire detection reduces the fire risk to occupants. So we can actually quantify the effectiveness of early warning system in terms of the reduction in the probability of casualties as demonstrated in our similar research. So the analysis of fertility rates, we quantify the life risk using what? A kind of metrics like the fatal casualty rate per fire. The fundamental relation is as the time occupants spends under the untenable condition, the casualty rates will increase. Therefore, to save lives, we must compress the timeline from ignition to safety. So the first and the most critical segment of this timeline is the discovery time. We can have several algorithms of the discovery time, such as the discovery time at what ignition. And we can have discovery time on the 5 minutes after ignition, then between 5 to 30 minutes after ignition, and then more than 30 minutes after ignition. So different discovery time will give us different life risk. So this is the theoretical model. Let's consider it like an evidence. So this data comes from an extensive UK file statistic reveal one of the most critical relationship in our fire safety. That is the direct link between the discovery time and the life risk. So we can see in table 1, look at the fatality rate per fire. In our single occupancy dwelling, if a fire is discovered at ignition, the fatality rate is relatively very low at around 0.0005. And if it is discovered within 5 minutes, it remains low. But if the discovery is delayed between 5 and 30 minutes, the rate nearly triple. So that means we need to discover our fire risk as soon as possible. And here we can introduce a very important parameter that is lambda. We will have the details of lambda, but we can calculate lambda by using what? By using the fatality rate and by using the difference between the fatality rates and the difference between our discovery time. So that will give us the slope. If we consider the fatality rate as the linear relation with our discovery time, we will get this lambda as our slope. So it is not a random but a clear trend. We can model this relationship mathematically, and this figure shows a linear relation between the fatality rate and the discovery time d. Here we use capital D to represent our discovery time. So the slope of this line, lambda, will quantify what? Will quantify the increase in fatality risk per minute of delay. So for a single occupancy dwelling, the lambda can be calculated as 0.00008. So how can we get this number? As we mentioned before, we use the fatality rate difference between the fatality rates, such as 0.003 and the 0.015, divided by the average discovery time. That means 7 minutes minus by 2 minutes. This gives us the slope of the linear relation, and it is also our fertility risk, the increase of the fertility risk per minute of delay. And we also have the K, parameter capital K. The parameter capital K means the intercept of the baseline. It represents the baseline fertility rate from other factors in the evacuation process. Okay, so let's have an example. If we have two identical fire in similar home, in fire A, a small detector alerts the occupant at 1 minute. That means D equals to 1. And in fire B, the occupant is asleep and discover the fire only at 20 minutes. That means D equals to 20. So using our model, the fatality risk in fire B is what? It's lambda times 20 minus 1. It's around 0.0015 higher. That means the fire B has a 1.5 percentage point greater risk of a fatality, which is a massive relative increase. So this quantifies the life-saving value of every single minute, right? So this pattern is not limited to fatalities. And this table for non-fatal casualty tells us a similar story. We can see the same sweep slope for early discovery on the 5 minutes, which has the lowest casualty rates. However, if for the fire discovered at the very moment of ignition, the rate is higher. So the note on the next step explain this. These are likely fire where the occupant is already in the room of origin and may be immediately overcome and involved in the ignition. The scenario that requires separate investigation. Okay, so this is our powerful conclusion for all this data. The statistics indicate that the value of early discovery is inducing casualty rates. So this isn't just a theoretical point. It is also a fundamental justification for our investment in early warning system. So the entire purpose of our smoke alarm, our heat detector, and our sprinkler, which can activate and signal an alarm before a fire, has a growing significance that can help us to shift the discovery time D from the right-hand side of the graph, where the risk is catastrophic very high, to a left hand that it is minimal. Okay, so building directly on the statistic evidence, we can now formalize a life risk model. So the risk module is a linear relation we have already mentioned. The fertility rate is equals to K plus lambda D. So we already understand lambda. It is the slope from our graph, quantifying the increase in fertility risk for every minute of delay in the discovery time D. And the other parameter K, capital K, is the intercept. So now we have several other parameters to calculate K. Firstly, we have some recognition time. It is represented by B, and we have the movement time represented by E, and we then have the tunnelability time represented by F. So we can have a look at how we combine it together. So this brings us to the core concept of the total evacuation time. So for a safe outcome, the entire process must be completed before the environment become very dangerous. So this is summed up by a critical inequality. The total evacuation time, H, is equals to D plus B plus E. and must be less than the tenability time f. So if the condition is met, the occupant reach safety in the time, and if not, they are exposed to untenable conditions. Since the occurrence of the casualty in a fire is a real event, so we can model its probability using our exponential distribution. In this slide, we have this kind of exponential distribution to model the probability of no casualty of any positive value. So the foundation concept here is that the occurrence of a casualty is treated as a real event, and its probability modeling use the exponential distribution as shown here. So we can break it down the equation by using the term T defined as the safety margin. What kind of the safety margin we can have? So the T equals to H minus F. It is our safety margin. And if T is negative, the occupant can reach the safety before conditions become very dangerous. And if T is positive, the occupant is exposed to a very dangerous condition for a duration of T. So therefore, the probability of the opposite outcome, one or more casualty, is simply 1 minus the survival probability, that is 1 minus exponential of minus lambda t. So the most important for the simplification, when we product the lambda t in a very, very small number, that means the risk parameter lambda is very low, or we have a very, very short exposure time. So we can use a kind of first order approximation for this exponential function. So this will give us the simple result that the probability of one or more deaths, PD, is approximately by using lambda multiplied by t, and can be also showing here use this kind of formula, because we have that t equals to h minus f, and we can always use d plus b plus e minus f to calculate the t. So in practical terms, this is a powerful formula for us for our fire risk assessment. It means that the complex and the dynamic process of a fire evacuation can be distilled into a manageable formulation. If we know that improving a building's alarm system will reduce what? Will reduce the recognition time, that is the capital B, by 1 minute, we can directly estimate the reduction in the probability of our what? The probability of our fatality as lambda multiplied by 1. So let's apply the model to see the impact of active fire protection. So this table compares casualty rates with and without protection. So we can look at the detector rows. By our installation detectors that reduce the average discovery time D from, let's say, 70.8 minutes to just 1 minute, the calculated fatality rate for multiple occupancy derailment decreased very significantly, and the value of lambda multiplied by h minus f will shrink dramatically. So this is a theoretical exercise, and also it is a kind of quantitative justification for our investment in our smoke alarm or our sprinkler, linking our engineering design to our life safe. So, as we conclude here, we must acknowledge the potential challenge for our fire risk assessment. Our model very is very powerful by using some of the probabilistic model or our life safety model, but the human behavior in fire is the largest variables, and it is not always predictable. So the data we use is from past fire, and the new materials and the building designs can create unpredictable scenarios. So while our life risk analysis provides a very important framework, it must be applied with some other professional judgment, such as a margin of safety and the humble awareness of its limitations. Okay, so this is the total content for our class today. And we begin by defining the fire risk, and we ending by quantifying its most dimension, the risk to our human life. So if you have any questions for our calculations or our models, please feel free to ask me. Okay, any questions? Okay, so that's all for our class today. And you can also find some guidance on the assessment tool of our topic selection and our topic presentation in Blackboard. I have published an announcement for your seminar group project. And you can take a look at it, and please feel free to send me email if you have any further questions. Okay? Okay, so have a good night.